there's another software out there called Julia, um, which is supposedly like, has all the benefits of MATLAB without the downsides of the cost. But the people who market Julia are the most obnoxious people in the world. Like they shove it down your throat. And so they're like, yeah, Julia, like they make it part of their lifestyle. It just makes it really like no one wants to use Julia, not because it's a bad software. It's a good software. I think people just don't like the people that are developing Julia. And that was like 5 years ago. So I don't know what the state of Julia is right now. It seems like it hasn't made any headway at all.
Hello, Dr. Chan. Can you hear me?
Yep, I can hear you.
Sounds good.
All right, it's 7 o'clock. Let's go and get started. Hi, good evening, everyone. How's everyone doing today? Doing good? Daylight saving, so I am admittedly kind of tired today. woke up way earlier than I should have today. Partially just because we have candidates coming in, so we're hiring 2 new faculty for next year. So I went to one of the interviews today, gave my input. Generally it's a good idea if you have the opportunity to help in the selection process of a new coworker. That's usually a good thing because you're going to be working with the person. So it's generally a good idea to make sure they're not like a fucking weirdo or anything like that. So it's good to go to those things. But I had to wake up really early for it, so I'm a little tired today. But I'm going to do my best to get through the lecture. Okay, so we have a lecture week, so we don't have no ANSYS activity this week, right? And so today we're going to be talking about meshing. Again, I know we've been talking about meshing a lot lately, and so this will be the last week. Okay? And so I call this set of lecture notes, I call it advanced meshing. And so because it's kind of more advanced topics in meshing, but it's almost like a smorgasbord of different topics. And more so than any other week than when we covered meshing, this is going to be a lot of ANSYS specific topics, right? I would say, for most of the previous weeks we talked about meshing, all that's pretty much true. All that's true in general, no matter what software they're using, whether it be ANSYS or Abacus or SolidWorks simulation, all that can be applied to that. A lot of what we'll talk about this week is specific to just ANSYS. So we'll talk about ANSYS features, ANSYS functions, what they actually mean, what they actually do. I'm sure there are analogs for this in other softwares, but a lot of the terminology and a lot of the way that it works, I'm going to be talking about specifically in ANSYS. Okay. And so, those kinds of things I consider to be more advanced because, now we're getting into kind of like software specific things. And, that's usually more advanced than kind of just the general knowledge. Okay. So remember, activity 4 is out there. So I think that was the last time that we met was activity 4, right? Remember, you have an extended deadline for that. So I think I give you 5 extra days for activity 4 relative to the usual deadline. Okay. And remember, that's just to make sure that, activity 4 is a little bit longer than the usual activity, but you guys also have the midterm project out there as well. Okay. So I know quite a few of you have already come talk to me about what you're thinking for the midterm project. So, that's really good. So it's good that you guys are thinking about it. You guys are running into issues. You guys are debugging. So if you haven't started yet, I would definitely get started with at least trying to run the simulation. Because that's going to uncover some issues, and then you'll have to talk to me. Okay, so definitely get started if you haven't yet, because it's doing the project is a lot of work. It's not just the simulations, but actually writing the report is going to take a while too. So you want to make sure you have enough time to not only do the simulations, but you have to be able to debug them for any of the issues that you run into, and then after that you have to write the report. And the report is more involved than just our usual activity reports too. So it's there's a lot more you have to write, there's a lot more formatting, you have to make it look prettier. Okay, and so, you want to make sure you have enough time for all that. Okay, so I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started with the lecture. And so today we're talking about advanced meshing. Our question is the project due after spring break? Project is due before spring break. So I think it's due the Sunday right before spring break. So not this upcoming Sunday, but the following Sunday it's due. Yeah. I want to have it due before spring break so that you guys don't have to worry about it doing it over spring break. And it gives me the spring break week to grade. Yeah. And then first thing we'll do after we come back from spring break is talk about the final project. And then you'll have until basically the end of the semester to work on the final project. Yeah. Okay, so advanced meshing. Oh, thank you. Yeah, so it's due on the 27th, which is the Monday of spring break. Yeah. Yeah, Sunday I think is when I have all my other classes. I have stuff due on Sunday, but yeah, your guys is due on Monday. Thank you for that. Okay, so advanced meshing. So, we've already talked about, and, we've already kind of seen throughout this class that meshing plays a very big role in your finite element solution, okay? And so we've gone over the basics of meshing. So we've talked about meshing quite a bit, as well as, some other kind of more intermediate topics. So things like shells and beam elements, okay? And so to kind of cap this off, like I mentioned before, I want to talk about meshing kind of more from a software specific side. So, how does ANSYS do a lot of meshing? So I've gone, throughout all the activities, you guys have asked me questions of, what does it mean to have a patch conforming mesh? What does it mean to have a patch independent mesh? What does sweep method do? What does multi-zone do? Okay. So we're going to cover all of that this week. So, a lot of the ANSYS specific stuff, we'll talk about it here this week. We'll talk about their pros and cons when you want to use one feature versus another. And basically how to really take advantage of all the features in ANSYS to really make your mesh good. Okay. Okay. Actually, like we said, is important. So most of the time, I'd say most of the manual time that you'll spend doing FEA is going to be working on the mesh. Okay. And so, once you get into more expensive simulations, like yes, the simulation itself is going to take, a lot longer than when you're going to be tinkering with it. But the amount of time that you actually spend, actually in the software, clicking things and modifying things, most of that time is going to be spent in the meshing. And so, it's really good to kind of, have a deep understanding of what meshing is, but also a deep understanding of, all the tools that are available. All right, so to start, I want to revisit a topic that we covered before, which is mesh quality. Okay, and I want to dive a little bit deeper into that. All right, and so mesh quality, we've talked about before. Mesh quality is kind of a metric that's used to assess, how good each of your elements are. And so it's an element by element metric. Okay, so each, when you mesh a geometry, you're producing a mesh with, thousands and thousands of elements. Each of those elements are going to have a score of how good they are. Okay? And so what we learned before was that generally speaking, you want to have elements that are roughly equilateral in shape. So their dimensions are roughly the same in all directions. And so generally speaking, if we just look at a 2D element, okay, 2D triangle, you want a triangle that looks like this, okay, where all the sides are about equal length and all of the interior angles are about the same as well. Okay? So this is a high quality my drawing is not high quality, and so I can't draw straight lines to save my life, but it's a high quality shape of triangle, right? And so if you compare that to a very low quality triangle, we've already seen this, but you may have a triangle that's highly skewed. So you might have a situation that looks like this. Okay. So this is a highly skewed, low quality all right, and the way that we kind of assess the quality of our elements is through a metric called skewness. Okay? And so skewness varies from 0 to 1. Where a skewness of 0 means that your element is not skewed, so this is high quality. Versus a skewness of 1 means that the element is highly skewed, generally low quality. Okay. And so there are benchmarks, and so there are thresholds that people like to hit in terms of skewness. And so in ANSYS, basically, they tell you basically the maximum, the minimum, and the average skewness. Okay. And so different people have different opinions on the threshold for these. So some people, said you have to have an average skewness less than 0.5, and you have to have a maximum skewness less than 0.95 and stuff like that. So, the kind of the real answer to that, and I know, if you look in the notes that I do have some numbers in there as well. But the general answer is that, the amount of skewness that you have in your elements, yes, a lot of it depends on the mesh settings that you're going to apply and how good you are at applying those settings. Yeah. And so, some of it depends on that, yes. But a lot of it is also going to depend on the specific geometry that you're looking at as well. And so if you have a highly irregular, highly complex geometry with lots of curves and stuff, and you can't really do anything about that, and so you have to model all of that, some skewness is going to be inevitable. And you're going to have an element with a skewness of 0.99999. You're going to, be wondering what you're going to do about that, right? You might have an average skewness that's actually over 0.9 as well, okay? That's okay, right? And so it's okay to have, some highly skewed elements, and on average, it might be okay too. Skewness is not really, it's not really like a black or white test, right? So it's not something that you can use to just invalidate a mesh or say this mesh overall is bad. It's just a metric to kind of tell you, how your mesh is doing. And so if you're looking at your simulation results and you're seeing that, you're getting some behavior that you may not be expecting, skewness may be something that you have to look at, okay?
Dr. Chan,
Yes,
I have a question.
sure.
So would this be the same as the Current number?
Oh, so you're asking about the Courant number? Yes.
Yeah.
So the Courant number is a little bit different. So that is more of a kind of a simulation, more of a simulation thing, more so than a mesh thing. And so when you have an unsteady simulation, you also have to not only select the grid size. So for the mesh, you also have to select a time step size as well. So
Yes, yes.
right. And so we haven't got into unsteady simulation. So I believe that's either activity 5 or 6. We might be doing it next week.
So they are not related, the Current number and skewness, or are they all related in some way, but they're not dependent on each other? Or
They're indirectly related. So
I see.
so specifically skewness is not directly related to the Courant number. And so the Courant number is more something, it has to do with the time step,
I see.
more so than the mesh. Yeah.
Thank you,
But
sir.
that is another metric that you can use. And so, the thing about computation work is that there's tons of metrics, and you can choose to listen to all these metrics, or you can choose to use them or not. So, what I'm saying is don't get too caught up in the metrics. And so, the metrics are kind of there to kind of help explain, a situation where, maybe you're not getting results that you're looking for. Maybe you're getting results that don't make sense. Yeah.
Sounds good.
Courant numbers. So it's COURANT. Yeah, I think we'll probably go through it once we get to unsteady simulation. So yeah, it's not relevant, or not too relevant. Right. And so you may be asking, so how do you know if a simulation is not giving you good results? Right? And so I kind of left that term kind of vague on purpose, right? Because having a simulation not give you good results can mean a ton of different things. Okay. But specifically, I want you guys to kind of start to look at your simulation results and start to recognize certain patterns in your results. And so, if you recognize some of these certain solution features, then maybe you should look at your mesh. So that's kind of what we're going to look at next. Okay. The good thing about ANSYS is that especially if you're doing a steady simulation, it's not that expensive to actually run. Right? And so I think the most expensive simulation we may have done in this class might have taken you maybe like 5 minutes. Okay. In the grand scheme of things, a 5-minute simulation is not that long. So you really have a lot of freedom to, try a simulation, see how it runs, look at the results, and then go back and refine some of the other parameters. Right. So that is a luxury, and that's a luxury that you should really take advantage of, especially when you're learning finite elements for kind of the first time. Okay. Because a lot of computational work, a lot of it just kind of comes down to experimentation as well. Okay. But you can't really experiment with things without really knowing what to look for or how to assess your results. So that's what we're going to do. Okay. Any questions on this? Okay. And so how do we assess whether or not our finite element simulations are good? Okay. So one thing that I always check when I'm checking my finite element results is to check the results of my derived quantities. And so remember, derived quantities are solutions or things that come out of your finite element simulation that may not be computed right away. So maybe these are things that are computed based on the original solution. Okay. And so the prime example of this, and the one that we work with mostly in this class is stress. Okay. Equivalent stress, principal stress, it's all the same. So you can check any of them. Or strain is another good one. Okay. If you're doing like a thermal simulation, a good derived quantity for that would be like the heat flux or the heat transfer rate. Okay. If you're doing fluid mechanics simulation, you might look at like shear stress, something like that. Okay. Okay. And so what's significant about the derived quantities is that they rely, or the way that they're computed, is they're computed based on the derivative of your primary solution. Okay. And so the way derivatives are normally computed, right? They're computed with something known as it's not exactly like this within ANSYS, but it gives you kind of the right idea. It's computed with something called a finite difference. Okay. And the way finite difference works is that you basically, if you want to compute a derivative, you basically take the difference of two solution values divided by the distance between the nodes. Okay. And so if you have kind of an element like this, okay, and I'm just going to use temperature for now, just to kind of make things easy. Okay. And so let's say we have nodes 1, 2, and 3. Okay. And each node has a temperature associated with it. So each node has T1, T2, T3. So let's say this distance right here, let's say this is L1. This distance right here is L2. This distance here is L3. Okay. And so if we wanted to compute derivatives, let's say we wanted to compute dt dx, okay? The way that we would compute this is through kind of a combination of the nodes in this element, okay? And so we do things like maybe T1 minus T3 divided by L1, okay? And maybe we take the x component of this, okay? Plus maybe T3 minus T2 divided by L2 plus T1 minus T3 or T1 minus T2 divided by L. This is L2. This one's okay. It's not exactly like that, but you kind of get the idea. So generally speaking, when you compute a derivative, you take the difference of the nodal solution values and you divide by a distance between them. Okay. Okay.
Dr. Tron,
Mm-hmm.
is this the only method that ANSYS uses to compute the derivatives, or are we allowed to change the methods such as from finite difference to finite volume? Or is that just instilled in the software, the finite difference method?
Yeah, it's not exactly like this, and so ANSYS definitely uses a more sophisticated method, but I'm using this as kind of an example to kind of show you, because I'm going to tie this back to skewness and why skewness kind of has an issue with this.
I see.
So ANSYS definitely uses something more sophisticated than this, but yeah, this kind of gives you an idea of what's done.
Is that known to the user, the direct method that ANSYS uses, or just the concepts, and ANSYS keeps secret the method because of?
I'm sure ANSYS is transparent about that.
I see.
Unless they're doing something very revolutionary, but I don't think this is not something they would keep proprietary.
I see.
I don't think they would. Yeah.
Sounds good, sir.
Mm-hmm. Yeah, so it's probably in their manual somewhere. And there's probably something you can change within the ANSYS interface itself. I'm sure they have a couple of different methods for it as well. Yeah. Mhm.
Sounds good.
Kind of the important feature that I want to highlight here is that whenever you're computing a derivative on an element, each of the nodes kind of should ideally contribute equally to the derivative. Okay, and that's why this is important to have an equilateral element, because if you have an equilateral element, then each of these terms here, okay, each of these terms will have kind of roughly the same magnitude. Okay, so they're kind of roughly the same contribution. Okay. If you have a highly skewed element, we compute distances as well. So let's say this distance is L1, this distance is L2, this distance is L3. Okay. So for a highly skewed element, you have some lengths here that are going to be significantly bigger than the other ones. Okay. Thus, when you compute the derivatives on these elements, you're going to have a very lopsided affair where, if you're going just based off the distances, right? So L3, since L3 here is much smaller than L1 or L2, any derivative that involves L3 is going to be much higher in magnitude, right? Because L3 is in the denominator. That, if in certain situations, that's going to dwarf, any contributions for T1, right? So any derivatives that involve T1, are basically going to be non-existent because, its derivative is going to be much smaller. Okay. And that's not good because, if you're computing something like a derivative, you want to make use of all the information that your element has to offer just in general. Okay. Sometimes this may not be an issue. So maybe there just isn't much variation in the T1 direction. Okay. And so maybe you can compute, even though it's a highly skewed derivative, maybe your derivative is still going to be accurate anyway because of the physics of the situation. Okay. But these are generally situations you want to avoid. So you want to try to make use of all the information that you can. Because even for the best element out there, the quadratic hexahedral, you only have, that's 20 nodes of information, right? When you compare that to your entire mesh, which may have hundreds of thousands of nodes, that's not a lot. So you want to make sure you try to use as much of the information as possible. Okay. Okay. Any questions on this? All right, so that's one issue that skewed elements have. It's skewed elements, when you compute derived quantities on skewed elements, it can be unreliable. Okay. Another issue that can affect that skewed elements have to deal with is if you have high solution gradients. And so if your solutions are changing very rapidly in the neighborhood of a skewed element, it may be difficult to capture that. Because remember, when we run FEA, right, and we choose an order for the element, what the software is doing is that it's making an assumption for how the solution will vary, over across an element. And so, let's even take let's start with the equilateral triangle. Okay. Let's assume that we have a linear element. And so if we were to graph, the variation between T1 and T2, okay, you're basically assuming that we have a linear line, right? So we go from T1 to T2, and there's a linear variation between the two. Okay. And so that's fine, if T1 and T2 are quite close to each other in value. So let's say T1 is like 25 degrees Celsius and T2 is like 25.1 degrees Celsius. I think having that linear assumption is okay. Okay. But if the distance between T1 and T2, our question, can you remind us what order of element is? Yeah, so the order of an element is basically the order of the interpolating polynomial, right? So remember, whenever you have an element, we have this the shape function that approximates the solution within the element. So a linear element will have a linear polynomial associated with it. Yeah. Mm-hmm. Okay. And so this is fine if T1 and T2. And so when you don't have very strong variations in your solution, it's having a linear approximation is fine. Okay. But there are situations where your solution is going to vary rapidly in that short period of space. Okay? And so let's say that you have a situation that looks like this. And so even for an equilateral triangle, so this effect is definitely made worse for skew elements, but you can even have this effect for equilateral elements as well. Okay? So let's say that we have a situation where T1 and T2 kind of vary very rapidly across space. Okay. Right, so with the linear element, we're going to assume that the variation between T1 and T2 is purely linear, okay? But maybe the true solution is not like that, right? So whenever you see kind of a high solution variation like this, you always kind of ask the question, what if the variation doesn't look like a linear line? Right? So maybe what if it looks like this? Okay? So maybe it starts out, the variation is kind of small and then it kind of ramps up very quickly at the end. Or even crazier, maybe your solution kind of pops up and down like this. So maybe it starts out really high, maybe go down low, okay? Maybe it comes up like that, okay? So a linear line is not going to be able to capture all these different variation patterns. So let's take this issue right here. Let's take this issue of high solution gradients and then throw a skewed element on top of that, where your derivatives are going to be, even more crazy, right? So your derivatives are going to be, computed even more wildly. Let's just say. Okay. And so what results from this, what you kind of visually see in terms of your results, is that you might see, things like the stress jump or oscillate between elements. Okay, so it might be very high in one element, and in the very next element might be very low, and it kind of jumps in between. Okay? So maybe you have a situation like this, right? Maybe elements kind of look like this. Maybe this is just one layer of the mesh, okay? But then in this layer, maybe you jump, maybe you have high stress in these elements. But then right next to it, you have kind of a deep blue for, deep blue for low stress. Okay, so the blue here, low stress. And the red, we have high stress. Okay. And so you see this kind of, kind of jumping of solutions. Okay. If your solution is that extreme, then that is definitely a cause for concern. Okay. A lot of times you're not going to see it to this extreme, but what you will see is that the solution kind of changes colors very abruptly. Okay. So that's always one metric that I look for when I'm looking at finite element simulations. And so I basically, one good eye test that you can use is that if you look at something like your stress distribution or even your deformation distribution, you should see kind of a smooth variation. So it should be kind of a smooth transition of, of colors. And so, even if you have an area where, you have stress highly concentrated, if you zoom in on that part, there should be enough elements in that area where the so the solution transitions smoothly between colors.
Um, Dr. Chan, so
Yes.
what you're implying here is that if we run an FEA simulation and there's no quote unquote blending, we should be, but we should take notice and see if anything is wrong.
It's definitely you should look into that. And so one thing you can do is you can probably the easiest thing you can do is just refine the mesh in that area. And so just go to that area of the mesh and just make the elements smaller. That should definitely help with the transition. And if that doesn't help, maybe you start looking at the quality of the elements. You look at the skewness and see if there's anything that you can do to fix that. So maybe changing your methods, maybe changing the element shape in that area. Those are things that might help.
So from someone who has experience with FEA, that's not that's not appealing, having areas of high how do I if if there's strong differences in color and there's no transition, um someone who has from an FEA experience standpoint, that simulation could be optimized to include
Yes.
transition. Is that what you're saying?
Yes, I would definitely look at that. And so, I mean, you see it all the time. And so having high solution gradients is not uncommon. And so, especially in the structural FEA space, you're going to have concentrations of stress in certain areas of your model. That's unavoidable. But if I look at those areas where the stresses are concentrating, I shouldn't see, one element with the stress of like 30,000 psi. And if I go two elements next to that, the stress just suddenly drops off to like, 20,000 psi. So that's a huge variation. And so I would definitely look into that. I would start by refining the mesh in that area, because then I start to question of, is that peak stress there? Is that really due to the loads that I'm applying, or is it due to the mesh not being a good quality in that area?
I see. Sounds good, sir. That somewhat helps me understand. Thank you. So
Yeah.
just refine the mesh if need be, if that occurs.
Yes. I mean, refining the mesh is just kind of good in general, because it not only makes the mesh elements smaller, which kind of helps with your accuracy, but it also helps make the elements higher quality in that region as well. So yeah, refining the mesh in those areas is usually a good.
Sounds good. Thank you, sir.
Mm-hmm. Yep. Okay. Any other questions on this? Okay. And so with that said, looking at the variation in colors, I think that's a good way to start. But ANSYS actually does something under the hood that kind of makes things not seem as bad. And so, ANSYS does something called solution averaging. Because ANSYS knows this too. So ANSYS knows that when engineers are looking at their finite element solutions, they know that those engineers are going to take those solutions and present it to their boss, or they know that a lot of students are taking these courses. So students are going to be taking their simulations and presenting to the instructor. Okay, and they know that what people are looking out for are things like this, right? So you want to see smooth transitions of your solution in general. Okay, and so ANSYS does something that visually makes it look like the solution is transitioning smoother than it actually is. Okay. And so what it does is it basically takes, what the colors that you see in ANSYS, it's not on a pure element by element basis, but it's kind of an average of kind of all the elements around it. And so naturally, whenever you're doing like an averaging process like this, it's going to smooth out the solution. It's going to smooth out the signal, right? And so things like a low pass filter kind of works in a similar way. Okay. So this is good if you want to produce a smooth looking solution. The fact that ANSYS does this is nice. But sometimes you don't want to get a smooth looking solution. Sometimes you want to find the issues in your model and fix them, right? And if ANSYS is doing this kind of automatic, just visual change, and this is just a purely visual change, it has nothing to do with the solution at all, it can be harder to actually find the solution. Okay. So one thing you can do is you can turn it off. And so when you're viewing your solution in ANSYS, you can view what's called the unaveraged stresses. Okay. And so by viewing the unaveraged stresses, you'll get a much better idea or much clearer picture of how, how quality your mesh is and whether you're having these kind of element to element jumps or these abrupt kind of changes in color. Okay. Better yet, ANSYS also has an output setting called structural error. And so this is one of the output fields that you can get. So things like like total deformation or equivalent stress, it's in that area. Okay. And so what the structural error shows is the difference in the strain energy field between the average and unaveraged results. Okay. And so generally what you should see is that if your mesh is a good quality, you shouldn't have that many differences between the average and unaveraged results, okay? Because if you have smooth transitions in your unaveraged results, then when you average it, it's not really going to make much of a difference because your transitions are already smooth, okay? And so one thing you can do, so this is kind of another way that you can assess your mesh quality, is to look at the structural error field and see if there are any significant differences, okay? And the best thing about this is that, not only can you see if there's significant differences, you can see where those differences are, and that'll give you some ideas of where you can improve your mesh. Okay. We'll go through this in the next activity. So the next activity, I'll show you how to use the structural error, and you can use that to improve your mesh. Okay. Any questions on this so far? Okay. So let's talk about stress singularities next. Okay. And so stress singularities are another issue that you need to look out for, when you're meshing. Okay. But the kind of the theory behind stress singularities actually has nothing to do with finite elements at all. Okay. And so if you follow elasticity theory, Elasticity theory predicts that when you have concave corners of small areas of curvature, the structural stress will concentrate in those areas. Okay? Most extreme case is when you have a perfectly perpendicular corner. And so for a perfectly sharp corner, the radius of curvature for that is 0. So for a perfectly perpendicular corner, elasticity theory predicts that the stress there will be infinite. So if you have, a sharp corner like this, we're going to have a very, very high stress at this corner. Assuming that this model is undergoing, a structural load.
Dr. Chan,
Yes.
for that drawing that you made there with the sharp corner, this is more of a solid mechanics question.
Yep.
Would that be okay, or would a engineer designer want to make that corner round to handle high stress?
Oh yeah. So I mean, normally, you want to avoid situations where you have sharp corners like this, especially for any kind of load bearing structure. And so if you have a load bearing structure, most pretty much day one of structural engineering will tell you you need to round.
Yeah, they want to smooth it out. Okay.
Yeah.
Thank you, sir. I was just wondering.
Yeah. No, it's a good question. And so what's interesting and why this is relevant for finite elements is that you see the exact same behavior in FEA as well. And so if you're working with a geometry that has a sharp corner, you're going to see stress concentration there. Okay. And why this is relevant and why this is relevant for meshing. Okay. Remember last time we talked about mesh convergence tests, right? And so when you have a mesh convergence test, you basically keep refining the mesh until your stress value or your deformation or whatever kind of converges to a steady state value. Okay. The thing is, with a sharp corner like this, you can refine the mesh all you want. You can refine the mesh until your computer, starts crying out to you, right? You're never going to get a converged value of stress. Okay? And it will keep amplifying it as long as you keep refining the mesh. Okay. Reason for that is very interesting. And so, whenever you overlay a mesh onto an object and you have a very sharp kind of small feature like this, the mesh kind of naturally kind of smooths it over because it's basically trying to fit an element to that sharp corner. Okay. And so let me draw another example down here. So let's say that we have kind of a Pac-Man looking thing, right? And so let's say that we want to put a mesh on this Pac-Man, right? And so if we have, a triangular mesh, it might look like this. Yada, yada, yada. Right? In other words, let me kind of get to this corner right here. And let me kind of write this a little better just so you can see. Okay. Okay. So in this corner, we're going to be making a mesh, right? And so you can kind of see what I'm doing here. So even in the case where you have a corner directly on a node directly on the corner, right? In the end, we get something here that kind of has a smoother kind of transition, so it's not as sharp. Okay? And so sometimes it's very hard to see, but a lot of times you just need a subtle change, right? And so in the worst possible case where it's perfectly perpendicular, you really will get infinite stress. That's how it's predicted, right? But meshing kind of helps you avoid that, ironically, right? And so meshing actually makes the solution not as bad, okay? But as you refine the mesh, that smoothing kind of goes away. And so, as you refine the mesh, you capture your geometry a lot more accurately, and any kind of smoothing like this, is eliminated. And so when you have sharp corners like this, you want to be careful about your mesh, right? If possible, hopefully you're not in a situation where you have to run an FEA on a sharp corner like this, right? And so if you can, I would go back to the CAD model and try to see if you can smooth out those corners. You add a fillet or maybe a chamfer, right? So something to kind of smooth it out so you don't have this perfectly perpendicular angle. Okay. Right. So even with a rounded corner, you still will see stress concentration in an area, but it's not going to be as extreme. Okay. And better yet, with the rounded corner, you have a much better chance of getting a smooth transition of stress in that corner rather than a sharp one like this. Okay. So an interesting story. So, activity 3, I know everyone's turned that in already. So activity 3 actually used to have a sharp corner like this. Basically where the signpost kind of attaches to the ground. And my students were seeing this exact phenomenon occurring. So they would go to activity 3, they would refine the mesh, they would keep refining it. They'd refine it until you can't even see the elements anymore. But they would still see that their stress just keeps climbing and climbing and climbing. Right? And so it's because of this kind of sharp corner feature. Okay. And so since then, so this is a change I made maybe about 2 years ago. I added kind of that fillet at the base of that signpost. You have a much better chance of getting a stress value that actually makes sense. Okay. All right, so definitely be careful of that. And so if you're, because I know, when you run simulations, generally we look at the maximum and minimum stress, right? You want to look at where the maximum stress is occurring. So if it's occurring at a corner, maybe your issue is not really has to do with the mesh, it has to do more with the geometry. Okay. Definitely be on the lookout for that. All right, any questions on this? Okay. Okay, so for the last 15 minutes today, I wanted to start talking about some of the more advanced mesh controls within ANSYS and what they actually do. Okay. So first thing I want to talk about is the difference between global and local mesh controls. So global mesh controls, I give it the name global because it applies to the entire mesh. Okay, so when you apply, the global mesh size or the global mesh order, that's going to apply for the whole mesh. Okay. And so the way that you can access the global mesh controls is through just the mesh itself, right? And so if you remember in ANSYS, when you create a mesh, there is like a top of the tree mesh object, right? When you create things like sizing and methods, those go underneath the mesh. But if you click on mesh itself, you can set things like the size, the order from that. Okay. So generally what I like to do, and everyone has a kind of a different style of doing this too, but generally what I like to do is I like to use the global mesh control to set a global size, right? So a lot of times, I just kind of based on the overall size of my object, I like to set a global size that applies for the entire object. And so, for example, let's say that you're working with the geometry and your geometry has, dimensions of maybe 10 centimeters in one direction, 4 centimeters in another direction, and 3 centimeters in that direction, right? So it's about 10 by 10 by 4 by 3. Okay. And so generally, you want to set your mesh size so that you have a good amount of density in all directions, right? Remember, we want to avoid the situation where we have just one element through the thickness. Okay? So what I like to do is I like to use the global mesh size to say, if my shortest dimension for my entire geometry is 3 centimeters, let me set my global mesh size so that, even in areas where I don't specify a local size, that I have at least 10 elements through that dimension. So let's set the global So maybe I set the global mesh size just as a starting point to be 0.3 centimeters. Okay. Just to make sure that one dimension doesn't get forgotten. So we have at least enough density in that direction. And so another setting that you can do. So this also has to do with size. And so maybe maybe your geometry is quite complicated and you can't really sum it up in terms of like a raw dimension. Okay. There's a global mesh setting called resolution. And so resolution will kind of be almost like the same thing, except it kind of simplifies it. Okay? And so the way it does that is that it does it according to a slide bar. Okay, and so the different resolution settings go from 0 to 7. So you can set it to be 0, 1, 2, 3, 4, 5, 6, 7. Okay. I don't know why they chose 7. It seems kind of an arbitrary number. Okay. But basically the way the slide bar works is that if you put the resolution down to 0, you end up with a mesh that's quite coarse. But then you put the slide bar over to the other direction to 7, you end up with a very fine mesh. And so for situations where you don't want to fuss, you don't want to set a direct size to the element, you can use this resolution slider to kind of do the same thing. Okay. This is also useful, if you want to do like a very basic mesh convergence test, right? So if you want to do a mesh convergence test, you can start with a coarse mesh, you can run your simulation, then increase the resolution 1 by 1 to see if your solution will converge by the fine mesh. And so if you're curious about how ANSYS kind of selects the size, I think they have some kind of algorithm based on the geometry of your object. If I haven't looked into it, but I'm sure they have it in their manual too. But if it works the way I think it works, what it does is that it looks for kind of the smallest surface in your model and then chooses the mesh size based on that. Basically, how many elements do you want through that base? Just because I know just in other softwares that I work with, that's how these things kind of work. Okay. Any questions on global mesh settings? All right, so global mesh settings are a great place to start. So when you're just kind of meshing your object for the first time, you don't really want to do a lot of local controls. I would say try the global settings first, see how the mesh looks. Okay, but you can always modify that with local settings. So local mesh settings. Just like the name implies, they let you modify the mesh in certain areas of the geometry, okay, and only in those certain regions. And so this is what we've been using mostly in our activities. It's specifically activity 3. Okay. And so with local mesh settings, you'll be able to make things like sizing objects, things like method objects, alignment. Okay. So those are just 3 examples, but of course there's a lot more settings that you can do. Okay. So if you remember when you made a sizing object or you made a method object with an ANSYS, you had to select a certain section of the geometry, right? Whether it be a surface or whether it be a part. Okay, and so that let you apply the mesh in those areas. Okay? And so what's important to remember is that whenever you apply a local mesh setting, whether you are increasing the mesh size or decreasing the mesh size, local settings will always override the global settings. And so whenever there's a conflict, the local settings always take precedence. Okay? And so one way that you can think about it is that, the global settings, use that to apply for, most of the mesh that, maybe for parts that you don't really care about. Okay, but for the parts that you really do care about in terms of where you expect the stress concentration to be, or maybe you expect the solution to vary a lot in a certain region, you can use the local controls to make sure that you capture those really well. Okay. All right. Any questions on this? Okay. So let's talk about hex dominant mesh. I think that's kind of been where a lot of questions during the activities are done. Okay. So hex dominant, if you want to get a hexahedral mesh on your geometry, this is the main way to do it. Okay. And generally, if you're able to get a hexahedral mesh, this is something that's desirable because they have better, kind of shape properties and they have better convergence properties as well. So hex dominant mesh will always converge faster than a tetrahedral mesh. Okay. All right, but the tricky thing is that it is difficult to get a hex dominant mesh. Okay. And it's still kind of an open question right now in the FEA community of how do we get a mesher to always produce hex elements. Okay. The way ANSYS does it is actually pretty clever. And so the way ANSYS does that is that it actually first creates a tetrahedral and triangular mesh. Okay. So ANSYS actually starts out with not even a hex dominant mesh at all. So it starts with kind of a regular mesh. Okay. And the good thing about tetrahedral mesh is that, just like we said before, we know that they're always going to work. Okay. And then what ANSYS does is that, after it creates this tetrahedral triangular mesh, it then is going to attempt to merge together adjacent triangles to make a rectangular and hexahedral mesh. So, let's say that we start with a mesh that looks like this. So this is our triangular mesh. Okay. So maybe this is the mesh that you have on a surface. And then what ANSYS is going to do is it's going to try to eliminate some of the element edges to form a rectangular mesh. And so maybe this edge is going to eliminate this edge. It might eliminate, maybe this edge as well. Okay, so it's not going to work everywhere. And so you're going to have situations where you're still going to have some triangles. But the idea is that most of the triangles or most of the tetrahedron are going to be merged together. Okay? And so maybe you end up with a situation like this. So you have instead 1A1 hexahedral element like that, another one like that. You still have one triangle on the edge. Okay? And same thing here. So maybe you have one triangle and one big hex, just like this. Okay. And so, of course, it's not going to work everywhere. So, if you, I think some of you have noticed in your additions of ANSYS that ANSYS will tell you the percentage of triangular or tetrahedral elements that are left. Okay? And sometimes it'll just flat out fail. So sometimes, it'll try to merge things together, and you're going to end up with a very skewed or very weird looking element. Okay? And so that's when basically errors occur, is when those situations happen. But that's basically how the hex dominant mesh goes. Okay. All right. Any questions on this? Okay. All right. So that's it that's all we have time for today. And so on Wednesday, when we pick this up again, we'll talk about other methods that you can use in ANSYS to create a hexahedral mesh. So hex dominant is not the only way. So we can have sweep method, we can have multi-zone. There's multiple ways that you can do that. So we'll talk about how they work and when are the best situations to use them. Okay. All right, so thank you guys for coming today. I know it's, on the clock, it says, we met at the same time, but this is a little bit earlier than we usually meet because of the daylight savings. So, hope you guys enjoy the rest of your evening. Hopefully you guys aren't as sleep deprived as I am coming out of the daylight savings, but, hope you guys have a good day. Thanks for coming, and I will see you guys on Wednesday.
Thank you, Dr. Chan.
Thank you, Professor.
Thanks, Ismail. Have a good day.
You too.
See you. Mohammed, any final questions? Okay, all right. So I'm gonna close up the Zoom room. So I'll see you Wednesday.